Hello, this is the third part of my series on alternating current, and in this video we are going to continue with our discussion that we started in the previous videos about alternating current. And we need to review a few things. First of all, when we're talking about alternating current, we're talking about a source of current, or we're talking about a current that changes polarity periodically. And the last video we started to talk about the most common way that the alternating current is generated, and it's usually through moving a conductor. We'll say that this wire is my conductor through a magnetic field. And one thing that I didn't mention in my last video, and I apologize, I'm kind of just going off of my head here. I don't have a lot of notes, and keep in mind this is from the perspective of an amateur. This is sort of a hobby for me, but anyway. So, as I mentioned in the last video, anytime that you have a movement of a conductor or a wire relative to lines of magnetic force, i.e. You have a conductor that's moving through a magnetic field, you're going to generate a voltage, and if you have a path for current to flow, then current will begin to flow as a result of this movement of or the cutting action of the conductor cutting through or cutting across the lines of magnetic force. Now, one thing I did not mention, which will become pretty important a little bit later, is the fact that just as a magnetic field can generate a voltage if you have a conductor moving through that field, a current flowing through a wire, a current flowing through a conductor generates a magnetic field. So these two, electricity and magnetism, are very closely related concepts. Now, we're going to come back to the first of those two ideas in this video, that is that you can generate a voltage by moving a conductor through a magnetic field, and then later it will become important the fact that a current flowing through a wire itself generates a magnetic field around the wire. So we talked about how that most of the electricity that we use today is generated through some type of a conductor moving through a magnetic field. And what I've done here is drawn we're going to say that this box that we have here, oops, let me zoom in on this just a little bit. This box represents there it goes, represents a magnet, okay, and it's got two poles to it. And we're going to say that this right in the middle is a conductor, and it's basically connected to a wire loop that spins around, and we'll make it clockwise, in a clockwise direction inside of this magnetic field. Now, these lines that I've drawn across from pole to pole, keep in mind this is kind of hypothetical. Actual generators operate in a lot of different ways, but this is just to sort of illustrate the point. Okay. Now remember, this all relates to the fact that when we move a conductor through a magnetic field, when it cuts across so-called lines of magnetic force, that generates a voltage in that conductor, and a current will begin to flow. Okay, so these lines that I've drawn across here that go basically run horizontally represent our lines of magnetic force, and of course the lines are actually much more denser than this, or more dense than this. This is just sort of an illustration of the principle. Okay, so we'll say that you're looking at it as if you're looking straight into the wire, basically. This little dot represents our loop, our wire, okay? And notice that right now at this 0 degree position, it's not really cutting across any lines of magnetic force because it's actually running parallel to the lines of magnetic force. But as it starts to move in this clockwise direction, notice that it begins to cut more and more through the lines of magnetic force, and by the time it's moved 90 degrees, it's essentially running perpendicular to the lines of magnetic force, so it's cutting the maximum number of lines of magnetic force, and thus is generating its maximum voltage. Okay. Now, in the last video, we put this on a graph that could look something like this. And remember, one of the keys to this whole concept of AC is that unlike DC, where as soon as you flip the switch, basically your voltage reaches its maximum almost instantaneously. There is a little, I guess what you call induction or self-induction in the conductor, so there are some factors that limit that first instant that you flip the switch. But basically, when you close the switch in a DC circuit, the voltage will reach its maximum almost instantly, which we represented with this would be represented by a straight line that just goes horizontally across the page, because the voltage level is not changing. And I don't know if you can see the numbers, but I've drawn this particular sine wave to a 40, where the 140 volts is the maximum. So that's what we're looking at right now. Sage, my dog's making racket. Go away. Go. And I don't want it to come on. It'll probably come through on the video. That's okay. Anyway, now with the sine wave, if we look back at our graph, since the voltage that's generated all has to do with the lines of magnetic force, that are being cut by the conductor, there are periods of time, for example, at this 0 degree position, when the conductor is moving parallel to the lines of magnetic force, so we essentially have a 0 voltage. Okay, but as this loop starts to spin around inside of this magnetic field, it's going to hit a maximum right here. Then it's going to start to go back down or diminish to 0 again, and then it's going to hit another maximum at 270 degrees in the opposite direction, and that's going to give us an opposite polarity on our voltage. So let's see how this plays out in our graph. Okay, so I've drawn essentially what you just saw, the spinning of the conductor inside of the magnetic field. I have graphed this where we have two axes here. We have a horizontal axis that represents the degree, the angle of rotation essentially. And then I have a vertical axis that represents the voltage levels. Okay, and so thinking back to our graph, notice that right here it's at 0 degrees. The conductor's running parallel to the lines of magnetic force, so there's no voltage generated. But as it starts to spin into its next position, 90 degrees later, it rotates 90 degrees. Now it's running almost exactly perpendicular to the magnetic lines of force, generating the maximum cutting action, and therefore this is going to be our peak voltage, our peak of 140 volts. Then it's going to go back down to 0 as it rotates another 90 degrees, and now it's parallel to the lines of force again, so it's not cutting across. And then it's going to start to go in the other direction and generate a voltage, but this time with an opposite polarity. This is all relative, but most graphs, they tend to make the the top side the positive voltage and the bottom side the negative voltage, but keep in mind that that's sort of a relative term. So it's going to reach its negative peak right here, peak voltage, and then it's going to go back down to 0. And at this point, when it is rotated a full, the conductor is rotated full 360 degrees, we now have one complete cycle of AC. And remember, we defined the term frequency as the number of complete rotations of our conductor per second. So if I had a signal that was changing its polarity, in other words, it was going from its positive voltage peak to its negative voltage peak, and it was making that change, let's say 1 million times a second, then it would have a frequency of 1 million hertz, or you could also say that it has a frequency of 1 megahertz, because the term mega means million, and so that's what, you know, in the field of radio, you often hear the term megahertz, and that's what they're referring to. So that's where that comes from. Now that we've sort of talked about how alternating current is generated, and another thing that I wanted to review here real quickly. So because this voltage is constantly changing, it's sort of hard to take a measurement unless we come up with some sort of an equivalent to the power that would be generated in our DC circuit, where we have a constant voltage that doesn't change. And if you'll think back to the last video, we mentioned that that is actually called the root mean square, or RMS value, and we talked about how that you could find that equivalent voltage. So let's go back over that quickly, those rules. Okay, so couple of different things here, and the other thing that I mentioned, I think, in the last one, is that I can also find out, because this signal forms what's called a sine wave, we can actually find out what the voltage is at any point along this continuum. So let's say that I wanted to know what the voltage was in my generator after, what did I put here? I think 38 degrees, no, 40 degrees, I believe. After 40 degrees of rotation. In other words, it's at the 40-degree mark. It's right before its first maximum positive voltage maximum, or peak value. Well, all I have to do to find that instantaneous voltage is to take the peak voltage, which we said was 140 volts, and then I multiply that using my sine function. Now, all the sine function is, this has to do with trigonometry. It's a lot of fancy hooey-pooey. But what it boils down to is it's a ratio of the sides of a right triangle, and you can use these ratios to sort of figure out different values, the length of the various legs of the right triangle. And so we're looking at this in terms of a right triangle, where our and what we're talking about here when we say angle of rotation, we're talking about, if you consider this to be our center right here, and here is one leg, let's say, of the right triangle, and then here's we're talking about the angle of rotation, but notice that we could draw this in such a way that it forms a right triangle. And all that the sine function is the ratio of the, the opposite side to the hypotenuse. So it'll tell us what that instantaneous voltage is at any given point along the continuum. Now, I chose 40 degrees sort of arbitrarily, but basically the formula is the same regardless of what angle of rotation you want to take a look at. And what you're going to do is you're going to take your peak voltage, in this case it's 140 volts, that's what it peaks out at after 90 degrees of rotation. We're going to multiply that by the sine. Usually you can find this on your calculator, and then just plug in your angle of rotation, 40 degrees, and we see that it's reached a value of about 90 volts. So it's not quite up to the maximum yet, but it's getting there. 90 volts after 40 degrees of rotation. Okay, and as I said, we really need a constant value that we can work with to use in equations, because if we try to use the peak value, the 140 volts, that's not representative of the complete cycle. Because remember, in an AC signal where it generates a sine wave, it's going to hit its peak only for just a very small portion of the total cycle. It's going to do that twice, once in the positive direction and then again in the negative direction. So what we need to do is find an equivalent value that we can use that dissipates the same amount of power in a resistor as a DC equivalent where the voltage does not change. And to do that, we use the RMS, root mean square formula, which basically all you have to do, is take the voltage peak and multiply that peak voltage by 707, and that'll give us our root mean square. Okay, you can also go in the opposite direction. So let's say that you know the average, or well, it's not exactly the average. The average is found a little differently, but the root mean square value, but you don't know the peak voltage. Well, you can find that by multiplying by the reciprocal of 0.707, or 1.414. So let's take our wave that I had drawn a while ago that has a peak voltage of 140, and let's multiply that by 707, and we'll find out what our RMS voltage is. Roughly it comes out to 98.98 volts, which we can round up for our purposes right now to 99 volts. Okay, now what's important about the RMS value is that we can use it in circuit analysis to figure out other values. So if I, let's say, have a circuit, that's one that I've drawn here, but instead of using a battery as my power source, I use a AC power source. For example, I plug it into a wall outlet which has an RMS value of 120 volts. Well, I can use that RMS value to figure out the current flow or any other values that I'm interested in finding out with regard to this circuit. So I've drawn a simple series circuit here that has a total of 3 resistors. And remember, for a series circuit, we're going to add those resistor values to get our total. But what I don't know is how many amps are flowing, how much current is flowing through this circuit. So I can just use the regular Ohm's law rules that we talked about in a previous video several months ago to figure it up. And what I'm going to do is I'm going to find my total resistance by adding the resistor 1 value, the resistor, let me put this so you can see it better, the resistor 1 value plus the resistor 2 plus resistor 3. I add all these up and it comes up to 600 ohms. Remember that resistance is measured in ohms. Now I can use my Ohm's law formula to find out the missing value. That is the amount of current that's flowing through this circuit. The Ohm's law formula states E equals I times R, where the E represents the potential or the voltage. Remember, it's just a difference of potential. It's the force, but not the flow of current itself. The I stands for the current flow, which is measured in amps, and the R stands for the resistance to current flow, which is measured in ohms. We're going to rearrange that formula just a little bit through algebra, basically, or just through arithmetic, and we've come up with the formula I is equal to E over R. Now, I know that my RMS value of voltage for this circuit is 120, but remember, with the voltage that's coming out of the wall on your outlets, your plug-ins, it's actually going to peak at about 169.7 volts, but the RMS value that's the equivalent of the non-changing DC value is about 120 volts. So that's what we're going to use. And all we have to do according to our formula is divide this out. So we take 120 volts, we divide that by our total resistance of 600 ohms, and we find that we have 2.2 amps flowing through this circuit. Okay. I believe I'm running pretty close to my time here because I don't really want to go past 20 minutes. But what we will do in the next video is show how I can use the RMS value instead of a DC voltage. This time I will use my RMS voltage for an AC circuit, and we can solve for current in a parallel circuit. And then we're going to go on and talk about some new concepts that really are not very useful so much with DC, but are incredibly useful and interesting when you have AC, when you're using AC. And I'm talking about the inductance and capacitance, which are in many respects are similar to resistance in a circuit, although there are some big differences, and we will talk about that in part 4 of this series that I'm doing to help my wife and I to understand all the theory stuff for ham radio on AC electricity. Thanks for listening if you did take the time to listen to this. Bye.